Hey friends, today we're going to talk a little bit more about integrals. So far we know that when you're doing an integral, you're finding the area under the curve. Fine. Or when you're doing the integral, you're finding the antiderivative. Fine. But what does this mean in real life? So let's get some real life applications today on how we can use integrals and what do they really mean. All right. So we talked a little bit before in class about this too, the two D words of distance and displacement, and we'll get there in just a second. But just in general, what did integrals mean? Area under a curve. Yes. What's the shaded area region? Okay. Or we're finding the antiderivative and plugging in numbers. Fine. But what else? So for example, let's say that V is a function and it's the volume of a water. It's the amount of water in a reservoir at some time t. Then we can say that V prime, the derivative of V, is the change in rate. It's the rate at which the volume changes, right? The derivative of V prime is the rate at which it changes. So how fast are we adding water or how fast are we taking away water? So if we do the integral of the rate, if we do the integral of the derivative, if we're doing the antiderivative of the derivative, it should go back to regular V, right? And you're right, it should go back to the amount of water. But if we're talking about two different times here, T1 and T2, we take our antiderivative here, as you can see, and like we've been practicing, we plug in T2 first on top and then T1. Notice what it is we're finding. We're actually finding two different volume amounts. So by taking the integral, by taking the antiderivative of the derivative, we're actually going to get the overall change in volume. That was what this integral is giving us. It's giving the actual change in volume. So V of T2 minus V of T1. So it's not just finding the area under a curve. Here, if we're talking about the amount of something, a lot of times it gives us the change in the amount over those two time periods between T1 and T2. This could be sort of the number of people that have arrived from T1 to T2. It could be the amount of air between T1 and T2. But when you take the integral of a derivative, you go back to amount. You go back to the amount of something. Okay, but now what we talked about before in class was back to particle motion, one-dimensional particle motion. So we have S of t, if you remember, S of t was position, and therefore S prime, which is V, is velocity. Fine, fine, fine. So now if we take the integral of the velocity, as you see here, it should shoot us backwards back to position, right? S of t, and it makes sense. But again, because we're taking the integral with limits of T1 and T2, and we plug those into our position, look what we're really finding. We're finding S, go backwards, S of T2 minus S of T1. That's the change in position. So between time equals 1 and time equals 2, what's the overall change in position? That means they traveled here and their velocity was positive or negative, whatever. But overall, between where he started and where he stopped, what's the overall change? How far did that particle travel? That, folks, is what we call displacement. So the integral of just the velocity shoots us back to position, but between those two different time periods, it's position here and position here. So it's your overall displacement. All right, displacement is just the integral of velocity between two time periods. So it's the overall change in position, or like we said, it is the displacement. So there's your big word there. Okay, but what if we want to find out exactly how far the particle traveled? So I know that it traveled this way. All right, so velocity is positive, it's going to the right. Velocity is negative, it's going to the left. So if we do that over and over again, how far did it travel? So I need to add up all of those distances that I traveled, no matter which way I went. That's distance. But in order to do that, as you see here, in order to find the actual distance in a time period, we have to take into account where he was going to the right, meaning where velocity was positive, and where it's going to the left, where velocity is negative. Because if you think about it, if we need to find the area under the curve, the integral of velocity, and if velocity is positive, you should have a positive area above the x-axis. But if your velocity is negative, if you're going to the left and your velocity is negative, he's below the axis, and your velocity area there, the integral, will be a negative area. We can't have that. That's displacement. I want to take all the negative areas and make it positive. So what we have to do here is we have to take the absolute value of velocity. So by definition, the total distance that a particle travels is the integral of the absolute value of velocity. If there's no absolute value there, then you're only finding displacement. If there's no absolute value, then you're finding displacement. But if you want to find the distance, we need to take the absolute value of velocity. If you're putting this into the calculator, it's very easy. Just use your absolute value button, plug in the integral, and you're good to go. But if we do it by hand, it is a little bit trickier because we have to take into account, like we said, where is it going, positive or negative? Look at this graph here. This is the graph of a velocity of a particle. So as you see at T1 here on the bottom left, you have this all the way to T2 on the right. Now as he travels, the overall here, the first blue area that you have here, the velocity is above the x-axis, so the velocity is positive, which means he's traveling to the right. And then as you notice, he starts to slow down, and as he becomes a negative velocity, he's going to turn, stop, and go this way and go to the left. And then again, as he hits 0, he's going to turn back around, and your velocity is positive, he's going to the right. So overall, he's gone really far to the right, a little bit to the left, and a little bit to the right. So he really went only about this far or so. That's your displacement. But if I want to add up all of those rights plus lefts plus rights, that's my velocity. So displacement would just be just the integral of just the velocity, no absolute value. So it's just going to be the A curve, the A1, the A3, and then the A2 is going to be negative. So it would be basically this. Okay, so we are taking into account the fact that it's negative velocity. It's going to be a negative area. So we're going to take away the area. Displacement is exactly what it looks like. But for distance, we're going to do the absolute value, which means any area, any velocity that's negative, we have to make it positive. So you have to take the absolute value. So imagine that this area 2 that you have here in the middle is actually flipped up here. So if we take it away from here and we make it positive, now A1 plus A2 plus A3, that's your actual distance. Okay, so what we really have to find here, it makes it a little bit harder, is we have to find where is our particle stopping and changing direction. Because then we have to know which ones do we have to absolute value. Some of these areas are already positive, like this one's positive and this one's positive. Do I have to absolute value it? No, not really. We just need to absolute value the ones that were negative. So we have to find those first, and then we'll absolute value and we'll do all the areas. Okay, let's actually try it, folks. So here's a good example problem here. And I'm going to switch into my other screen so we can practice it together. All right, hang on just a second. We'll flip screens and we can work on this problem together. Displacement versus distance. All right, so your big clue here, first of all, is it says particle. So you know that you're in particle motion. It's traveling along a line. So the velocity is here for time t. We've got units, so keep paying attention to that because we always want to include our units in our answers, meters per second. All right, let's try number 1 here, friends. Find the displacement. Great. Okay, we know displacement is just the integral of the velocity. No absolute value, right? But we need limits here. So let's check and see. All the way at the end of the problem says from 1 to 4. Okay, so I'll put from 1 to 4. Great, let's do this one by hand. We can do it. So this is the integral from 1 to 4 of our velocity. T squared minus t minus 6 dt. Okay, so by hand, we got to take the antiderivative. So that's going to be 1/3 t cubed minus 1/2 t squared minus 6t. We don't need a plus c because this is a definite integral, not an indefinite. And we're going to evaluate this. I'll use my little evaluation symbol here from 1 to 4. Okay, now remember which one we plug in first. We're going to plug in the top one first. Then we'll plug in the bottom one and we'll subtract our 2 answers. So this becomes, how about, let's do the first one with all the 4s in it. We're going to do 1/3 4 cubed minus 1/2 4 squared minus 6 times 4. All right, that's the first part with 4 plugged in. Then we're going to plug in 1. So we get 1/3 1 cubed minus 1/2 1 squared minus 6 times 1. We'll take those 2 answers and we're going to subtract them. All right, so we got some annoying fractions, but we can do it. We get 64/3 minus 8 minus 24 there. And then over here we have minus 1/3 minus 1/2 and minus 6. All right, looks like we're going to have to find a bunch of common denominators with 6. So let me just take all of our fractions if I can and put them together, and I'll take all our non-fractions. So we have 64 thirds. And then over there, we had negative 1/3. So I'll bring him over. I have a minus 1/2. So that gives him a positive 1/2. And then if I take negative 8, negative 24, and minus a negative 6, that should actually give me, I think, minus 26. Sounds good. All right. So these together will actually give me 63 thirds, which is actually 21. Which is actually 21. I'll put there in parentheses. Minus a third. Oh, sorry, minus a half. Minus 26. So once I take that 21 minus the 26, I get negative 5 minus a half. Common denominator, we get negative 11 halves. All right, so what we just found right now is the overall displacement. We took the integral, the antiderivative velocity, which gets us back to position. So in terms of units, if the velocity was meters per second up here, then the actual length, the displacement would be negative 5.5 or negative 11 halves meters. Okay. Oh, let me make a quick fix here, folks. I just noticed that I changed my plus a half to a negative half over here. So let me add a half here, add a half. I'll change my answer. I blame Zoom. So you should get negative 9 halves meters. I believe that's right. Check my math. But overall, that's what we do. We take the antiderivative of just the velocity, no absolute value, and we're good to go. That means between time equals 1 and time equals 4, I ended up backwards. I ended up negative 4.5 meters from where I started. Okay, that's part A. Now, when we find the distance, part B, this is the more involved problem. So we want to find the distance traveled during the same time period between 1 and 4 over here. Okay, so I need a new page for this one. My velocity again was t squared minus t minus 6. Like we said, this particle is going to be traveling a little bit to the right, and then maybe a little bit to the left, a little bit to the right, but we need to add those all together. So we need to figure out which ones are negative so I can make it positive, so I can add all positive areas. So I need to know where this thing changes direction. So let's go ahead and do a sine chart or a sine graph. Because our idea is, where is it left? Where is it moving left? Okay, well, if we set this equal to 0, we should be able to factor it very nicely. And we're good. All right, that means t equals positive 3 and negative 2. Great. Well, time can't be negative, right? So we did beautiful algebra here, but we just can't include that number because that doesn't exist. This is in our time period from 1 to 4, so we are going to include it. So now when I go to my sine chart here, I have t equals 3. I'm going to stop it here at t equals 0, right? Because we can't have negative time. So let's try to figure out from 0 to 3. Remember, we just plug in some test values here and here. And let's see, it changes direction at 3, but from right to left or left to right or some combination. Let's see. So if I plug in 1 again into my derivative factored here, into my velocity factored, I should get a negative times a positive. This overall would be negative. If I plug in 4 into my factored velocity, I should get positive times a positive. That means it's positive. So it looks like from 0 to 3, it's going to the left. And from 3 on, it's going to the right. Okay, so because it's going to the right from 3 on, we don't need to worry about making that integral positive. It's automatically going to be positive because the velocity is positive. But here's the one we're going to need to change. Okay, so here's how we do it. We need to break it up into separate integrals then. So the integral from 1 to 4 of the absolute value of velocity, that's distance, right? The absolute value. So what we have to do is we're going to break it up into separate integrals. We notice that from 0 to 3, our regular velocity goes one direction. And then let's add the other one from 3 to 4. Now, let me double check. I think the time period on the previous page said 1 to 4. So let me actually change this bottom limit over here, 1 to 3, and then 3 to 4. And I'm stopping at 4 because that's the time interval from 1 to 4. All right. So we're separating into two different integrals because one integral he's going one direction and the other integral he's going the other direction. So which one was negative, which one was positive? Do you remember? We said that from 0 to 3 it was negative. So this integral needs to be absolute valued. That will make it from negative to positive. If we want to, we could take the separate integral and also make it absolute value if you want, but it's already positive. So that's sort of redundant. You don't have to. So we break it into separate integrals so we can take into account the fact that it could be negative, could be positive. And let's just continue now. We're going to take the integral of the first one, but we're going to take our answer and make it positive. So we're going to take our integral from 1 to 3 of t squared minus t minus 6 dt, but make it positive, plus integral from 3 to 4 of t squared minus t minus 6. And I don't need to make that positive because it's automatically positive because our sign chart told us so. Okay, the good news is you're taking the same antiderivative twice, so it's not that bad. Okay, absolute value of, here we're doing 1/3 again, same antiderivative. And here we're taking this from 1 to 3, absolute value of it, so it becomes positive, plus, let's do the same thing. How about 1/3 t cubed minus 1/2 t squared minus 6t, and we're going to evaluate this one from 3 to 4. Okay, folks. So the rest of the math is pretty easy to do. It's just plugging in again all these numbers, but just make sure when you get over to this integral over here, make sure your final answer, you take the absolute value. So that becomes positive. And the one over here, because the velocity was already going to the right, the velocity was positive, we don't have to change that one. So that's going to be automatically positive. When you eventually add these two integrals together, you have found the total distance. Okay, so I'm going to leave the tough math plugging in for you because you're AP, you can do it, but I just wanted to show you the steps. One more time to review before we go. Displacement in part A was just the integral of the velocity, no absolute value. So if there's negative and positive, that's fine. We add them all together, whatever happens, that's what you get. When you do distance, we need to take into account where it is negative. So we need to figure out where is our velocity negative so we can absolute value that interval of the integral. So make a sign chart to determine where's your particle moving to the left, where's velocity negative. Then when you split up your integral according to your sign chart, absolute value the one interval where your velocity is negative, and then proceed as planned. Everything should work out. Hope that works out okay for you folks. And that's how we do a little bit of integrals in real life and what it actually means. All right, good luck, and we'll see you next time.